I'll join them and then I'll make a connection. So then here current I, which is flowing, the same current I, it has to flow. So if you see the practical, suppose that this is a cell, and these are the two wires, no? So can you join them? So this iron, copper wire. So we'll get a junction here. So there what happened is asking, assuming the current density to be uniform throughout the cross section, calculate Q. So what current flows, if you connect ammeter here, what current flows here, the same current has to emerge through this. So therefore the current in both the regions have to be same. So the resistivity of them here, these are called like a boundary. This is called like a boundary. So current is same area of cross section. So what should be the current density? Has to be same. Okay, this is a given diagram. Okay, we'll take the. I think something we have to take help of the formulas, the basic formula. So what do you expect if area of cross section is same? Take like this. I think that this will be better idea for you. Know. And look at the area of cross section of the wires. This is A, this is A. So what do you expect current density? It has to be same. And how we define the electric field inside it. This will be E1. This will be 2. Why different electric field? So we know J is equal to E by E1 by rho 1 in the first region. In the second region, E2 by rho 2. So in the current density, J1, J2 better right. So I'll J1 equal to J2 equal to J, which is I by A. So equating these two, E1 by rho 1 equal to E2 by rho 2. Not density, the resistivities. Rho means here the resistivities. So look at the field here. So suppose say here field is E2, E1. Go back to electrostatics. So let me assume here a surface, thin surface, actually boundary. This will be like a, I'll assume a surface here. That boundary only, let me bring it here. So there's a boundary, no? No, okay. Get this boundary, no? So this is that boundary. So this having a surface. So here we are having electric field E2 and this is E1 and let A be the area. I think I'm giving better picture, no? Let A be the area. Can you say anything about flux? If E1 equal to E2, what flux entered, that much of flux has left, no? You have to recollect some ideas of the electrostatics here. How many lines of force will enter? Those many will leave. Net flux through the surface. Through the surface, I'm not net flux through. There are two surfaces are there. Surface 1, surface 2. Will I agree? How many 10 lines will enter? 10 lines will leave. Net flux is 0. But here E1, E2 are different. A is same. So flux linking the left surface and right surface are different. So what is the net flux through the surface or through the strip? better you can call, or through the disk. Whatever if you want, you can call it. There's a boundary, net flux through the boundary. E1A minus C2A. Now what is E2? E2 should be rho 2 E1 by rho 1A minus E1A. E1A I'll take outside. Okay, there's a net flux. So then there's a net flux through the boundary. So net flux is non-zero. So there should be equal to charge enclosed by this one. So this equation Q by epsilon naught. Okay, I got this one. But E1 is what we assumed it, no? What are given thing for us? Current I and rho 1. How to eliminate E1? So go back to, so what is J1? You can write I by A. So in place of E1A, what you can write it as? I rho 1. So Q by epsilon naught. E1A should be equal to I rho 1, rho 2 by rho 1, this one. So what is the charge enclosed? This should be equal to I epsilon naught. Now, where do this charge should be deposited? It should be here. So if you want, I had to show the charge like this. These are the boundary conditions. So that's why in a lab, no, we'll never go for using more than wires of different material. Like this accumulation of charge will occur at the junction. Okay, at our level, only we have found out charge. At most of the equipments, no, that particular charge should not be deposited inside the equipment. Any reason? Like that particular charge, you know, it's a static charge here. That one. When you switch off equipment, so what that static charge? It has to flow, no? So even when you switch off the circuit, this current I will become zero. Then the static charges, what will happen? It will flow to the earth. Then what will happen? That is called like a transient currents. Go back to RC, RL, RLC. So there we saw like some like a static charges or some residual energy stored in the circuit will flow. That is what this one here. Very dangerous. Huh? They own these things only will damage equipment. Where do this will occur? In television, mobile, laptop, everywhere. This particular deposition of charges will occur at the boundaries. So minimum number of boundaries have to be there. It's very dangerous. More boundaries are there, definitely the lifespan of equipment will come down. It is having so much of sequences here. The designing has to be done such a way that the boundaries should be minimized. That's what it's telling. At our level, just it's a numerical, but electrical, electronic equipment, there's a very serious problem.